When faced with a triple integral, depending on the integrand and the region over which we're integrating, it may be more useful to switch to a different coordinate system, and this is the beginning of that. Triple integrals in cylindrical coordinates. A point x, y, z in the rectangular coordinate system has a representation r theta z in the cylindrical coordinate system, where r and theta are the same as those in the polar coordinate system. In other words, these are really polar coordinates. We're just throwing in a z coordinate as well. So x equals r times the cosine of theta, y equals r times the sine of theta, and z equals z. We also have that x squared plus y squared is equal to r squared, and the tangent of theta is equal to y over x. Cylindrical coordinates tend to be useful when the region D is circular. That's not the only time, but this often happens with cylinders and paraboloids, and sometimes spheres. I'm saying sometimes spheres because in the next coordinate system we're going to look at, it's spherical coordinates, and you're going to see a sphere, and you're going to want to use spherical coordinates, but sometimes we would use cylindrical. Really, I think it depends on maybe how the integrand looks and the region D in a coordinate plane. The triple integral in cylindrical coordinates, well, we start with rectangular. The triple integral over E of f of x, y, z dv is equal to the integral from alpha to beta of the integral from h1 of theta to h2 of theta of the integral from u1 of r cosine theta r sine theta to u2 of r cosine theta r sine theta of f of r cosine theta r sine theta z r dz dr d theta. That r is showing up because of what we know from polar coordinates with r dr d theta. We're going to start out by looking at a solid. We're going to sketch a solid described by the inequalities. Theta goes from 0 to pi over 2, and z goes from r to 2. Theta going from 0 to 2 means that in the xy plane we are only considering something in the first quadrant. R equals z, that's the one we have to deal with. Z equals 2 is easy, that's a horizontal plane, 2 units above the xy plane. As for r equals z, or really we would say z equals r, z equals r is, well, if we convert to rectangular coordinates, it would look like z is equal to the square root of x squared plus y squared. You may recognize that as the equation of a cone, or the top half of a cone anyway. So what we're going to do is we're going to take a quarter of the top half of a cone, and it's a quarter of it because we're only above the first quadrant, and represent that in R3. So I'll just draw this kind of arc of a cone. I need to show that it doesn't go all the way around, so I'm going to draw little segments here that are intended to be parallel to the x and y axes, and then turn it into a cone. So I'll give it some little roundness here, little flat top so we can see that. This is z equals 2. The trace in the xy plane would be part of a circle of radius 2. And there you have it. Now we're going to evaluate a triple integral over E of z dv, where E is enclosed by the paraboloid z equals x squared plus y squared and the plane z equals 4. First, I'd like to represent this region in R3. I have here the paraboloid and the plane, which is giving it a vertical top face. And for working with triple integrals, it's very useful to consider a region that is a projection in a coordinate plane. In the coordinate plane, the xy plane, we have a circle of radius 2. That's what would indicate to me that I want to use cylindrical coordinates. As far as limits of integration, we know that z will go from x squared plus y squared to 4, which in cylindrical coordinates means z is going to go from r squared to 4. The region D is a disk of radius 2, and for that disk, r is going to go from 0 to 2, and theta is going to go from 0 to 2 pi. Our integral then becomes the integral from 0 to 2 pi of the integral from 0 to 2 of the integral, now we're at the z level, from r squared to 4 of z, which is fine in cylindrical coordinates. If this was an x or a y, we'd have to convert it, of course, times r dz dr d theta. Please go ahead and integrate this and then come back when you're done. Integrating with respect to z first gives us the integral from 0 to 2 pi of the integral from 0 to 2 of 1/2 z squared evaluated from r squared to 4, and we'll still have the r dr d theta to deal with. Then substituting 4 in place of z squared and then r squared in place of z squared and subtracting, we get the integral from 0 to 2 pi of the integral from 0 to 2 of 8r minus 1/2 r to the 5th, that times dr d theta. There's no theta in our integrand, so we can quickly integrate from 0 to 2 pi d theta gives us 2 pi. And then using the power rule, we get 4r squared minus 1/12 r to the 6th. That'll be evaluated from 0 to 2, giving us a result of 64 pi over 3.